In last video, we have seen the Bohr's atomic model. In this video, we are going to discuss the emission spectrum of hydrogen or line spectrum of hydrogen. When hydrogen gas at low pressure is taken in discharge tube and the light emitted on passing electric discharge is examined with the spectroscope, the spectrum obtained, it is called as emission spectrum of the hydrogen. Now, according to Bohr's theory, an electron neither emit energy nor absorb energy as long as it stays in a particular orbit. However, when an atom is subjected to electric discharge or high temperature, an electron in an atom may jump from the ground state to the excited state, that is the higher energy state. Since the lifetime of electron in the excited state is very short, immediately it returns to the ground state, that is lower energy state, and during such a jump, energy is emitted in the form of photon. Corresponding to frequency or wavelength of each photon emitted, there is a line in a spectrum, emission spectrum, and it gives the emission spectrum for the hydrogen. Now, atomic spectrum of hydrogen shows large number of lines, and these various lines are grouped into 5 series, that is Lyman series, Balmer series, Paschen series, Brackett series and Fund series. Now, how this Lyman series is appeared? First is Lyman series. Now, as I said, when electron jumps from lower energy level to higher energy level, it absorbs the energy, and lifetime at higher energy level is very short. Immediately it come back to the lower energy level or ground state. Now consider electron jumps from the ground state to next higher energy level, that is n is equal to 2. Now from n is equal to 2 level, when electron come back to ground state, one line, actually it emits the energy in the form of photon, and that emitted energy shows a line in the emission spectrum. Okay, that is the line spectrum of hydrogen. In this way, when electron come back from n is equal to 3 to n is equal to 1, there is another line. When it comes back from n is equal to 4 to n is equal to 1, separate line is appeared. So in this way, these different lines appear at a particular portion. Okay, so that is the Lyman series. So remember, in Lyman series, electron jumps from any higher energy level, that is n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5, 6, 7 to n is equal to 1, and such a series of line, it is called as Lyman series, and these lines appear in ultraviolet region. So this is about the Lyman series. Now Balmer series, it is the group of lines produced when electron jumps from n is equal to 3, energy levels with n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, n is equal to 7 and so on to n is equal to 2. So here lower energy level is n is equal to 2. So electron when jumps from any higher energy level to n is equal to 2, then the lines appeared are called as the Balmer series lines, or these are in Balmer series. So these lines lie in visible region. Balmer series lines appear in visible region. Now third series is Paschen series. Similarly, in case of Paschen series, the lines appear when electron jumps from n is equal to 4, 5, 6, 7 to n is equal to 3. N is equal to 3. And this Paschen series lines appear in infrared region. Next is bracket series. So bracket series lines appear when electron jumps from the higher energy levels with principal quantum number equal to n is equal to 5, 6, 7 and so on to the n is equal to 4, and we get corresponding lines in emission spectrum which are shown here. Bracket series lines also appear in infrared region. And fifth series, that is the Fund series, these lines appear when electron jumps from higher energy levels with principal quantum number equal to n is equal to 6, 7 and so on to n is equal to 5, and we get corresponding lines in emission spectrum. This Fund series also appear in infrared region. So in this way, the line spectrum of hydrogen contains 5 series: Lyman series which appear in UV region, Balmer series which appear in visible region, Paschen series, bracket and Fund series. These 3 series of lines appear in infrared region. Now summary of this point is, Lyman series, for Lyman series, lower energy level is the energy level with principal quantum number 1. So here n1 is equal to 1, and electron jumps from any higher energy level with principal quantum number equal to 2, 3, 4, 5 and so on, and it appears in UV region. For Balmer series, lower energy level is 2, that is n is equal to 2, and electron jumps from any higher energy level with n is equal to 3, 4, 5, 6, it appears in visible region. For Paschen series, n1 is equal to 3 and n2 is equal to, that is higher energy levels are 4, 5, 6, 7 and so on, appear in IR region. For bracket series, value of n1 is equal to 4 and n2 is, that is higher energy level is 4, 5, 6, 7, 8 and so on, appear in IR region. And for Fund series, lower energy level or ground state is 5, n is equal to 5 or n1 is equal to 5, and value of n2 is 6, 7, 8, 9 and so on. It also appear in infrared region. Now the wave number or frequency of line in line spectrum of hydrogen, it is calculated by using a Rydberg equation, and the Rydberg equation is nu bar, that is wave number, or wave number is directly proportional to the frequency. So wave number, it is reciprocal of wavelength. It is equal to R. R is a Rydberg constant. Its value is 109677 per centimeter. So R into 1 upon n1 square minus 1 upon n2 square. This equation is important. This is the Rydberg equation. And by using this Rydberg equation, we can find out the wave number. Number of spectral lines in the line spectra of hydrogen, it is calculated by using equation, or number of spectral lines equal to n2 into n2 minus n1 upon n2. So n1 is the ground state energy level and n2 is the excited state energy level. It can be any 2, 3, 4, 5, like that. So this is about the Rydberg equation. Now quickly we'll solve one example so that point will clear. Calculate the frequency and the wavelength of radiation in nanometers emitted when an electron in the hydrogen atom jumps from third orbit to the ground state. In which region of the electromagnetic spectrum will this line appears or lie? Rydberg constant is given 109,677 per centimeter. Now here Rydberg formula is, Rydberg equation is nu bar, that is wave number or frequency, it is equal to R into 1 upon n1 square minus 1 upon n2 square. Now Rydberg constant is given. Now here n2 is 3 because here it is mentioned that electron in the hydrogen atom jumps from third orbit, that is n2 is equal to 3, to the ground state. For ground state the n1 is equal to 1. So for a ground state principal quantum number is 1. Lowest energy level is the ground state. So here n1 is equal to 1 and n2 is equal to 3. Now just substitute the values in this Rydberg equation. Nu bar, it is equal to 109,677, this is the Rydberg constant, into 1 upon 1 square, this is the value of n1, minus 1 upon 3 square, this is the value of n2. So this is equal to 109,677 into, when we solve this, it comes 8 by 9, and when we solve this, answer is 97490.7 per centimeter. So this is the nu bar. But lambda is equal to, that is wavelength is reciprocal of wave number. So it is equal to 1 upon 97490.7. So it is equal to 103 into 10 raised to minus 7 centimeter. This is the wavelength in centimeter. So 1 nanometer equal to 10 raised to minus 9 meters. So just convert this centimeter to nanometer. So wavelength, it is equal to 103 nanometer. So 103 into 10 raised to minus 9 meter, this is equal to 103 nanometer. First of all, this centimeter, it is converted into meter. Okay, 1 meter equal to 100 centimeters, and then this meter, it is converted into nanometer. Now as wavelength is 103 nanometer, it appears in ultraviolet region. Actually this is also, we can find out the frequency also, and it is 2.91 into 10 raised to minus 15 per second. But from this answer we come to know the wavelength calculated lies in ultraviolet region, therefore line belongs to Lyman series. This wavelength, it belongs to ultraviolet region, and therefore it is a Lyman series. Line belongs to Lyman series. There is one more answer we can find out. Frequency, it is velocity of light upon lambda. We know the velocity of light, we know the wavelength. So velocity of light upon wavelength, we get this frequency. So this is about the emission spectrum of the hydrogen.